Okay. Okay, so let us start your snapping views of fluid mechanics. So first of all, just tell me, how do you define the streamlined body and the bluff body?
Okay, sir. Actually, the streamlined body is the body in which the uh, which aligns to the streamlines of the fluid flow.
Hmm. Okay. And what about the bluff
And
body?
bluff body is something like uh, something like a spherical ball which is not at all being aligned in the line of the streamlines of the fluid flow.
Hmm. Okay. And how does the shape of the body affect the boundary layer?
Mm. Shape of the body is the boundary line.
Yes. Do you know what is the meaning of boundary layer?
Ah, yes, sir. Boundary layer is a thin layer of the
Hmm.
fluid which is present nearby the solid surface, which is responsible
Hmm.
for the shear stress present in the fluid.
Okay. Tell me the name of some parameters which affects the boundary layer thickness.
Like fluid density, fluid viscosity, and depending upon the length, which we characteristic, like if we take a external flow over a flat plate, means we
Hmm.
need to take the length of the plate, or else in case of the pipe means we
Okay.
need to take the diameter. These are the some of the parameters which affects the boundary layer
Okay.
thickness.
Okay. Let us suppose if the boundary layer thickness, let us say if the kinematic viscosity of the fluid is very large. Okay. In
Okay.
that case, what will be the impact on the boundary layer thickness?
Actually, boundary layer thickness delta is given by in what is inversely proportional to root of Reynolds number.
Hmm.
So the Reynolds number is inversely proportional to kinematic viscosity. So if kinematic viscosity is very large, means the boundary layer thickness will be large.
Okay, that is okay. No need to worry. Okay, let us suppose if there's a flat plate which is placed in a flowing fluid. Flowing fluid.
Which is placed
Okay,
in
there's a formation. There is a flat plate. Okay, which is placed in a flowing fluid. Now, here
okay.
I'm assuming that the boundary layer is forming. Okay. So now tell me, how does the pressure gradient varies across the length of the flat surface?
Which one, sir? Shear stress. Uh,
Pressure gradient.
Actually, normally we assume the pressure gradient is almost zero, which means dou P by dou X is almost equal to zero. So that
Hmm.
this is the assumption which we used to take in the formulation of the boundary layer.
Okay, so according to you, the pressure gradient is zero over the across along the length of the plate. Now let us
Zero
say,
pressure gradient.
okay, let us suppose if I maintain the negative pressure gradient over the surface, negative pressure gradient over the surface, okay,
Okay.
in that case, what will be the impact on the boundary layer thickness?
Which means negative pressure gradient. Sir, I think the boundary layer thickness will decrease.
Why so?
Uh, because if the pressure gradient is more negative means we are sucking the it's something like we have the flat plate and then we
Hmm.
can assume the such as the porous medium we can suck the fluids in the boundary layer so that the negative
Hmm.
pressure gradient is being developed so that the boundary layer thickness will start to decrease because of sucking the fluid from the flat plate due to the porous medium.
Okay. Okay, that is okay. And how do you define the pipe?
Uh, Pipe is something like okay, it is just a uh, body which is used for allowing the fluid to flow from one place to other through the pressure potentials between the two ends.
Okay, and what are the different type of losses which occurs in the pipe?
First, there are two different losses which occurs. One is the major loss and another one is minor loss. The major loss will have the impact every time because it is due to the frictional effects which is present inherent in the fluid, because every fluids have the viscosity, so it will produce the shear stresses which creates the frictional losses. This is a major loss, and there are some minor losses like expansion, contraction, and due to some pipe fittings, and then there is a sudden orifice. So due to that, there will be kind of a minor loss which will be present, which minor loss may or may not present, but frictional losses in every natural process will be present.
Okay. Okay, that is okay. Do you have a pen or paper right now with you?
Uh, just a minute.
Yes, sir. Just take a pen or paper. Just arrange a pen or paper.
This whiteboard is visible.
Okay. Okay, you are using whiteboard. That is okay. Okay, let us suppose if you have a container. Okay.
Okay.
Let us suppose if there is a container and and at the bottom we have a horizontal pipe installed at the bottom of the container. We simply have a container in which the horizontal pipe is attached at the bottom. Not a horizontal pipe.
Oh,
The pipe is horizontal
okay.
from the side, from the left side or right side. You can make a
Okay,
horizontal
sir.
pipe.
Okay.
Yes, 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 like this. Let us suppose the length of the pipe is capital L. Okay, it is having some length. Now, if the container is holding some amount of liquid, let us say up to height capital H.
Okay,
Now
sir.
tell me, what will be the total energy of the fluid at the exit of the pipe if I have to consider all the losses here, major as well as the minor losses?
Okay. So first of all, I need to take the points 1 and 2. So according to Dolon's equation, P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus G plus Z2 plus frictional losses itself plus minor losses. So
Mm,
pressure 1 and 2 is atmospheric, so that I can cancel easily. So this area of 1 is divided by area of 2 is very greater than 1, so that I can cancel this thing also. And Z2 is this level, reference level. So I can cancel this also. So this becomes H is equals to V2 square divided by 2G plus frictional losses, which is given by FL V square divided by 2GD plus there is a minor losses which is
mm,
present due to the here action contraction.
okay,
So this contraction, if I assume the loss in the terms of coefficient, it will be like this.
okay. And what will be the exact value of the total energy? Here you have calculated the value of H. Now I just want to know the exact value of the energy at the exit.
Okay. So first of all, if I take this major loss means I can assume this as a laminar flow.
Mm,
So frictional F is given by 64 divided by RE, and the length is also given, and then this pipe has some diameter D. So this can be found easily, and then this loss coefficient. I think it would be around zero point 0.5. I think so, sir. So that we can able to calculate the velocity at the exit. Hello, sir, can you
yeah,
hear me?
I'm just saying. Yes, yes, yes. Now it's audible. Uh, I'm just saying that that is okay. That the head is equal to the kinetic energy plus some major losses plus minor losses here. Okay, but I am saying what will be the exact energy, exact value of the total energy, the
Total
analysis.
energy means you are mentioning that the EGL, right? Energy gradient like that.
Yes, 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 yes.
Energy gradient line will be something like it will be declining. It will be reducing somewhat. This the reduction is due to the losses which is present during the pipe
Yes.
flow.
Now tell me, now according to the AGL, okay, now tell me what will be the total energy at the exit according to this AGL as well as the head
Uh,
of the
i-
gradient.
at the inlet, it will be equal to P1 by rho g plus V1 square by 2g plus
Hmm.
Z, which is H. This is the EGL at inlet of pipe.
Okay. Okay, that is okay. And what will be the HGL here? Just draw the HGL with red color.
Okay. HGL. HGL is given by only pressure P by rho g plus Z. So that mm, I think it starts from here and then it ends here. Because in this point, this V1 square is almost equals to 0 because due to this highest area ratio, so that it will be equals to HGL at inlet.
Okay.
But in the end, we
Okay.
have the kinetic energy, which is V2 square divided by 2G.
See, see, you are doing some mistake here. Actually, the total energy of the fluid at the exit is going to be zero here. Okay. Why so? Because the analysis which you have done is perfectly correct. There is no need to worry. Here, the V square by 2G is the exit losses here. Okay. I accept that we have a kinetic energy at the exit, but we are not utilizing it. That it is going to be considered it is going to be considered as the exit losses here. So if you draw the EGL or the sorry, if you draw the TEL for the energy gradient line or the HTL, they are going to be meet at the longitudinal axis of the pipe here. That means the total energy is going to be remain zero at the exit. Okay, that you have to understand.
Yeah. Okay, okay, okay.
Okay, and the difference between these two is the v square by two. That is all. Okay.
Okay.
Uh, Next, now tell us some of the assumptions of the Bernoulli's theorem, Bernoulli's equation.
Bernoulli's theorem, the one of the assumptions is that it is a use is applicable only for steady flows, incompressible flows, and then it's only applicable for along the streamline, and it's applicable only for inviscid fluid, which means the viscous effects are being negligible.
Okay. Can we write the Bernoulli equation for the compressible fluid also?
Compressible fluid, okay, sir.
Yes.
This one, sir.
Okay. What will be the expression of the Bernoulli's equation for the compressible fluid?
Which means after integration.
Suppose, okay, that is okay. Okay. Is it possible not to write the Bernoulli equation? Just tell me yes or no.
Yeah, we can able to, if you assume the density remains
Hmm.
constant, we can able to reproduce
Hmm.
the normal Bernoulli equation.
Okay. Okay, that is okay. And what is kinetic correction factor?
Kinetic correction factor is it's just a factor which is used to implement, I just said, so kinetic correction factor is given by integral of UQ dA divided by U average A, which is usually used to take uh, when we are assuming the fluid is the ideal situation. So that we need to use the actual, if we want to use the actual kinetic energy, we need to incorporate
Mhm.
this kinetic correction factor into this into this equation.
Mhm. Okay, let us suppose it is a pipe and the fluid is flowing through it. Okay, and here I am assuming that the pressure head is equal to 5 meter and the corresponding
Uh,
velocity head is equal to 10 meter.
just a minute.
There is a
That
pipe
is the
and
pipe.
in which the fluid is flowing. Okay, and I'm just providing you the information regarding the head. The pressure head is 10 meter,
Pressure head is 10 meter. Okay.
10 meter, and the velocity head is equal to 5 meter,
Velocity head. Okay.
and we have a potential head as 10 meter. Velocity head
Kinetic
is
head is
5 meter, 5 meter.
5 meter. Okay.
Now, if the value of the kinetic energy correction factor is 2 here, then what will be the total energy of the fluid?
Kinetic correction factor is 1.2
Kinetic,
exactly.
kinetic energy correction factor is 2.
Okay. So, suppose if we are taking this points 1 and then points 2,
Mhm.
I can write the Bernoulli's equation as to P1 by rho g plus V1 square by 2g plus Z1, which is equals to P2 by rho g plus V2 square by 2g plus Z2. So we need to use this kinetic correction factor in the kinetic equation, which is alpha. This is the kinetic term
Hmm. Okay.
we need to use here. So alpha is to present here.
Okay. 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 Just tell me one thing. What is the meaning of head in fluid mechanics? What does it represents?
Actually, the fluid is something like a substance which is deformable under the action of shear stresses. And then the mechanics is about used to study how the fluid will be moving from one place to other, whether it may be static or dynamics. Statics means it will be concerned about the fluid, about rest, about the hydrostatic forces acting on the surfaces, whereas the dynamics is about how much the forces is being impinged on the surface due to the fluid flow.
Hmm. Okay. Okay. And what is cavitation?
Cavitation is a phenomena when the fluid is uh, flowing through a flowing through a medium where the pressure is much below the vapor pressure, so that the
Hmm.
fluid got actually the liquid got vaporized into the gas bubbles because of saturation temperature and saturation pressure. And when these bubbles enter into the high pressure region, these bubbles collapses and it fits the surface so that the surface may be eroded. This phenomena is called as the cavitation.
Okay. Okay, that is okay. And where do you find this phenomena? On which devices?
Mostly when we are working with a very low pressure region like centrifugal pump impellers, turbines, where we uh, where the blade experiences the low pressure region, the cavitation phenomena is the predominant.
Okay. Okay, that is okay. Let us suppose if you have a central pump,
Okay.
okay, and you want to make sure that the cavitation doesn't happen in that. Then what are the minimum requirement you will follow to make sure that the cavitation doesn't happen?
Suppose, yeah, let's say,
Hmm.
suppose if I have the pump, which is a centrifugal pump, and then where I am taking the water from the ground, this is the atmospheric pressure, and
Hmm.
then this is the delivery head. This is the suction head and then delivery head. So first of all, I would like to, so I will just check the total length, which is static head
Hmm.
plus dynamic head should be less than 10.3 meters. Because
Static plus dynamic. Okay.
this 10.3 is that this 10.3 is arrived from the P atmospheric pressure, uh, which is converted into the head form, which is 10 into 10 power 3 Pascal divided by density of water is almost 1000, and
So
then this is
according to
almost
you, so
9.3.
no, according to you, we cannot increase the pressure by above 1 bar. That's what we are trying to say.
No, no, no. We can use the pumps in series so that we can able to deliver the water
No,
above 10.3 meters.
let us suppose if there is a pump, you have a single pump. Okay.
Okay.
Then tell me what will be the range of the pressure ratio of a single pump? If I take a centrifugal pump or a reciprocating pump, whatever you want, what is the
Okay.
range of pressure ratio?
Um, range of pressure ratio. Sorry, sir, I'm not aware. Okay.
Okay, what is NPSH?
NPSH is the net positive suction head, which is given by uh, head due to the atmospheric one, and then static minus of dynamic minus of losses, frictional losses to suction and the friction losses to
Okay. Okay, Shivan, so let me provide my feedback. See, first of all, just you are preparing the fluid mechanics. Okay, so just prepare the boundary layer thickness, the streamlined bodies, and the plug body very well, very carefully. Okay, that's a very, very important topic. And after that, just go through the knowledge equation, the Navier-Stokes equation of motion. Okay,
okay,
and the fluid machinery part is very, very important because the most of the question can be asked from the pump topic itself, specifically the NPSH part. And what are the various design parameters of the pump or turbines? We have to understand that properly. Okay, so just go through the various characteristic curves that we study in the
okay,
hydraulic
sir.
machines because this subject deals with the practical applications of the fluid mechanics. Okay, so just go through that particular topic very well. Okay, and the remaining else which you
Okay,
have
sir.
provided
Okay.
me the answer are almost correct. Okay, but you need some revision in terms of the cavitations as well as the in terms of the flow through pipe. Okay, because when I'm asking you regarding the energy lines, the energy line which you are showing me, it is not correct. Just draw it up with the proper scale.
Oh,
Okay, and by the just by looking the energy line, you can tell me the exact value of the energy at whatever point you're calculating. Okay, so just go through this topic one more
okay,
time.
sir.
Okay, do you have any doubt here?
Okay, sir. Okay. No, sir, nothing, sir.
Okay, okay, sure. Now you can submit it. Okay.
Thank you. Thank you.